All right, so thanks everyone for joining us to talk about Platinum today. Let's hope it's fine. Before we do that, please, Adrian, quick introductions.
This is not working.
If the clicker works. Got a clicker issue.
Oh, clipper. Oh, OK. So this is me. So I'm Adrian Bataille. I'm with Magent since 2 years, senior consultant, and I'm based in France, Nice. I have 10 years of experience in cybersecurity, mostly in incident response, malware analysis, and threat intelligence.
Thank you. So myself, Matt for Friends, been doing this for a while, also part of the incident response team, just like Adrian, and with a stint in the Middle East. So with this out of the way, and with the legal disclaimer too out of the way, just to make sure we're all safe here, let's go right to it. So from an open source point of view perspective, while we were researching what we were seeing while defending one of our customers, we had two big blips on our radar, and both were Microsoft reports. The first one was a report going back to April 2016 in which Microsoft depicted a threat group targeting Southeast Asia, using their own custom tools, backdoors, and utilities. They were keyed as being very low profile, tight OPSEC, and as an example of operational skill set, Microsoft highlighted the fact that they were using hot patching as a means to inject code. Right? Second blip in the radar came at a very interesting point in time, June 2017. We were in the trenches or in the front lines right at that point in time fighting Platinum. So this was great for us because it explained also what we were seeing. Here, Microsoft highlights something called Intel AMT serial overland, which is basically a technique by which Platinum can communicate to a backdoor running on a server and bypass any operating system, firewall or security feature in place, right? Actually, you can go ahead and disable your network interface, and Platinum will still be able to use AMT serial overland to communicate to the backdoor and steal all your documentation, which is fairly interesting. Bit of context here. As usual, as happens pretty much all the time, we got a phone call, we parachute someone like Adrian somewhere in the world, and we start supporting our customers. So in this case, our customer had seen a few blips on their own radar in the SOC. We parachuted in, deployed our technology, and very quickly we confirmed, yes, customer is indeed compromised. And we were seeing Metasploit, Zeek, Shell, some port forwarding using P-Link. Nothing too exciting, to be honest. Everything was pretty low tech. The attacker was noisy. We really thought it was going to be a relatively boring engagement, right? But we were clearly wrong, right? So just a bit of background on how we approach investigations. We always deploy two key pieces of technology. One on the endpoint, which is our HX agent, and potentially our HIP agent if we have a live attacker. And the second one is the deployment of PX sensors to get us network telemetry, right? And we combine both of those in a loop. So basically, we start sweeping the environment, searching for indicators of compromise. When we find something on a host, we pull a lab response package. We build new IOCs from whatever we find there, and we continue again until we fully scoped the incident, right? Throughout this whole work, we engage with Flare, which is our professional reverse engineering team, and which, as you will see now, played a key role throughout the whole engagement. So, as I said before, we thought it was going to be a boring engagement. Low-tech attacker, noisy attacker, not really interesting for us, to be honest. We were wrong, right? The first sign we saw about it were these two command lines. We observed the attacker running these two command lines here, which, in a nutshell, alg.exe here turned out to be a renamed copy of the RAR file archiver. So what you're seeing is the attacker compressing and encrypting with password QWERTY both our HX agent and our HIP agent, which didn't make sense with the attacker profile that we had, right? Low-tech attacker, noisy attacker, why would they actually go ahead and try to copy our agents? It didn't make sense at all. So we pulled a live response package from the system. One of our analysts looked at that and came back saying, look, there is a piece of malware here. I don't know what it is. I don't see it persisting. And something is clearing PowerShell logs regularly on the system. So we basically grabbed all of these files, which were sort of blending in as 7-zip language files, and we sent them to Flare, which came back to us saying, hey, we've got a new piece of malware, a new family. We're going to call this Red Pepper.
Yeah, so Red Pepper was the first of several malware that we found tied to this threat actor. As Matt said, at first we didn't know how it was persisting. Eventually we found out that it was using WMI to persist. Specifically, it was using a filter called 7zip32 to blend even more with the 7-zip team. And that filter would trigger a consumer, which would execute PowerShell code on the OS boot. So that PowerShell code would basically decrypt one of those text files, then load it in memory, and it was shellcode, which would decrypt and load another text file, which was the final backdoor, which we named Red Pepper. So Red Pepper was a pretty big backdoor. And as every backdoor, it has a configuration file encrypted in triple DES. It also communicates to its C2 server using triple DES. All of the keys that it uses are unique to each sample. And it can also use HTTPS to evade most of our technology. Red Pepper has working hours, so it will only work from, for example, 9 to 6 to blend in with the user activity. It has a self-delete timer. So if the C2 does not respawn after 30 days, the malware will simply delete itself from the system. Finally, we ran Microsoft's ERR rule set. So in their reports on Platinum, they have a set of rules at the end, ERR rules. So we ran it on the malware, and it did not hit on this malware. But we eventually found out that it was actually an evolution of one of the malware that was described in the reports called ADB-UPD.
Yep. So we had one piece of malware. First question is, where else do we have this backdoor in a customer environment? So as we usually do, we set up all sorts of different hunting strategies to actually try and find the same backdoor on different systems. To begin with, we went for some of the easy, low-hanging fruit, just searching for known file names the attacker has been using. That tends to work sometimes. It never works if you're against a threat actor with good OPSEC, which was the case with Platinum, so that wasn't effective. The second thing we used is we noticed the payload had a unique export name that we could potentially leverage. Now, the problem was the payload was encrypted on disk, so we're not going to be able to find that searching on disk itself. It was just encrypted. Now, we could search that using a memory audit, but again, the problem is Platinum OPSEC was too tight. So we're not using Windows PE loader to load those DLLs, so we're using a custom loader, which basically meant that the DLL was not showing as such on injected processes. So, bad luck for us. Last but not least, we could always just search for specific strings in memory, but that turned out to be very noisy, right? There's this thing called Windows Defender, which is a hosted service. So what you're going to get if you get hits in there that are part of those signatures are basically hits on SVC host process. And the triaging cost for any of those hits is too high to make it really worth our time to go ahead and use that as a technique, right? So we fall back to checking for persistence, right? WMI that Adrian just showed you, or the consumers that Adrian just highlighted, those were really good, and those really worked for us, and we'll see that in a minute. We also searched for base64 encoded PowerShell with some constraints or limitations there. And finally, one thing which was really, really good from a signal-to-noise ratio was just actually searching for the event ID generated as a result of someone clearing the PowerShell event log. That doesn't happen too often. It certainly didn't on this and many other environments that we've used this IOC for, right? So again, really good signal-to-noise ratio. Finally, on the real-time side of things, our HIP agents was really useful there because of the obfuscated PowerShell detection, right? That automatically pointed us to systems of interest that were compromised. On the network side, of course, as Adrian mentioned, Flare had decrypted the configuration files, so we had the C2 IP addresses, so those were tasked immediately. But we don't expect it to be really nice, right? Again, Platinum, really good OPSEC, probably different IPs all over the world. And finally, what was surprisingly useful were user agents, right? Nowadays, every single browser auto-updates all the time, pretty much every day, right? So it was really, really useful from a detection perspective just to use some of the hard-coded user agents that we found here. So what we got back with all of that, we got back many things, right? The most important thing we got initially was a 64-bit version of Red Pepper. In this case, blending in as WinRAR. The other one was blending in as 7-zip. The 64 version was blending in as WinRAR. But we also found other pieces of unknown malware using a similar loading technique, okay? Some of these, like the Bonjour support, we could never retrieve. They were gone from the system before we pulled them. Some of those, like this table text T-service, DLL, we recovered and we sent through Flare. And Flare came back to us saying, hey, we got a new family, we're going to call this Red Curry.
So Red Curry, which we later found out was known as KB by the malware authors, was using the same loading technique as Red Pepper, so WMI and several base64 encoded files. That's basically how we found it. The final payload of Red Curry was packed. And when we unpack the malware, you will get this screenshot here of IDA Pro, which is basically an obfuscated, very obfuscated file. And if you're like me, and you like using hex rays for decompiling code, well, basically you get an error message, so that doesn't work. So it makes things harder. But, fortunately, we have Flare we can leverage. And Flare quickly found out that this was a keylogger used by the attackers to record keystrokes and encrypted files on their victim machines. So we found several versions of Red Curry. Each one of them had a different file name, different path, and different encryption keys for the actual keylog files. When we ran the Microsoft TR rule sets on this malware, we finally got a hit this time, and it was identified as Win32 plaque keylog_B, which basically confirmed that we were indeed dealing with Platinum. So our hunting strategy with Red Curry was basically the same as Red Pepper because it was loading using the same technique. The main difference was that Red Pepper was the files were encrypted on disk, whereas Red Curry, the files were only base64 encoded. So we could actually add a search for base64 encoded MZ files on the environment.
So this stage, we went back to some of the other more generic sweeps that we always run, no matter who we're chasing in an environment. This one was basically focusing on two specific Windows artifacts, shim cache and AM cache data. We're not going to drill into the artifacts. A very inaccurate description, but useful, is the fact that they just record everything that runs on the system. So we tend to go to those because they, again, signal-to-noise ratio there, depending on what you're searching for, can be really nice. And you're also going to find traces for malware that's gone on the system, right? Malware may have been deleted by the attacker, but this specific forensic trace is still going to be there. So we search again for every single known bad file name that we'd seen. Again, with Platinum, that turned out to be something really useless, right? Again, good OPSEC, so this didn't yield results for us. But we did notice that this ALG.exe that we saw on the first slide, that renamed WinRAR, it turned out to be that whatever operator we had on our environment used this ALG.exe as a default kind of file name. So whenever they had to bring any non-crucial, binary into the system, they just called it ALG, or he just called it ALG, right? So what we did is we basically pulled a live response package, and every system where ALG.exe had been executed, okay? And it proved really useful, right? The most interesting piece that we brought back was this thing here, something I was blending in or mingling with a legitimate Cisco VPN client. It wasn't loading as Red Pepper or Red Curry, so it was something different, something strange. We didn't really know how it was loading at the beginning. And again, it went through Flare, and we had a new name, which in this case was Red Salt.
So Red Salt, probably one of the more interesting backdoors that we found, maybe the main backdoor which was used by the attackers. So first of all, the persistence was interesting. First time I found that kind of persistence. I was using ACI shims. And in a nutshell, ACI shims are fixes that Windows can apply to executables which are loaded. This was introduced with Windows Vista, I think, for compatibility reasons. And there are a lot of different ACI shims out there which can be abused by malware authors. And one of them is called inject DLL. And that fix, that Windows fix, inject DLL, actually simply injects a DLL into an executable that you specify. So the attackers here were using this inject DLL fix to inject their malicious DLL every time the Cisco VPN executable was being launched by the user. So this first DLL, which was basically 95% junk code, had little bits and pieces of malicious code inside it, which would do some simple things such as decrypt an encryption key, decrypt a file name, and then load that file name, decrypt the file, and execute the file. The second file, which was loaded, is what we baptized Red Salt. So we found several versions of these ACI shims. Each one was tuned to the actual workstation which was being targeted. I think we found up to 7 different versions. When we ran the Microsoft ER role sets on this malware, we also got a hit for one of the Platinum malware, which was called Win32 Plagon. So back to Red Salt. Persistence-wise, well, we had seen ACI shims, but when we analyzed the code, we saw that it could persist through other means that we were not seeing, which were Windows services, COM, WinLog on notify events. We also saw traces of old bootkit code, which would not work on the most recent version of Windows, but this was just showing that the attackers had used this as a bootkit on older engagements. For the configuration, Red Salt can have its configuration as a file on disk or in registry. Each entry is RC4 encrypted, and the keys, of course, change for each sample. And for the communications, it can communicate using a more traditional mode, basically by beaconing out to its C2 server. And then it can also use a passive mode where it's listening for incoming communications, and this is where things get interesting. So Red Salt opens a raw socket on the host. So it's basically receiving every single communication and packet that the host is receiving, and it's decrypting every packet. And it's looking for a magic password to trigger an action which will enable it to decrypt the rest of the payload of the packets, looking for a port that it has to open to allow subsequent communications to happen. So with this functionality, Red Salt can actually proxy its communications with other Red Salt implants. So it can be used by an attacker to go further in a network if it's segmented, for example. And with this, these communications, it can use IPv4, IPv6, and also we found out AMT serial over LAN. So that was very interesting. Finally, this passive mode is compatible with a tool that Microsoft referenced in their report, which was they called the ZC tool, which I'll show some screenshots of in a couple of slides. So when Microsoft described the serial over LAN functionality from the Platinum file transfer tool that they saw, in their case, it was the file transfer tool was importing a DLL called imrstk.dll, and the tool was using the DLL's APIs to interact with the serial over LAN functionality. For Red Salt, the attackers were, I don't know, maybe more clever, but in any case, it was much easier. They basically got a handle on COM3, which is the default port used by serial over LAN. So they assumed that serial over LAN is configured on that port, and they simply, once they have that handle, they use the API's write file, read file to communicate using that functionality. So it's actually pretty simple when you think about it. So originally, we had a demo of the ZC tool communicating to a Red Salt infected VM, but for time constraints, we had to remove it, so there's only some screenshots left. On the top left, you see us using the ZC tool as a client communicating to a VM. And the tool is pinging Red Salt on port 445, which is always open on Windows. And it's then showing the password, DCC test 2018, and it's telling it to open port 3389 for the communications. Once you do that, the tool does all the that's needed for you, and you get your command prompt on the malware, which is Windows PC2. I then execute the HP command, which is the Red Salt command to list the available commands, basically like a help command. As you can see, as a help command, it's not very explanatory. For example, the RS command stands for reverse shell, so this shows all the commands that you can run on Red Salt. The PN command on the left is one of the more interesting commands, because here I'm telling the first Red Salt VM to contact the second Red Salt VM so that I can proxy commands through the first one to the second one. So again, it's asking me for a transfer port, a probe port, and an IP to connect to, and a password. And then once that's done, I'm connected to the second VM through the first VM. Finally, the bottom right screenshot is just an example illustrating the attacker's OPSEC. So here I'm in the reverse shell command prompt. I'm executing a del command, Windows delete. But if you notice on the bottom, it shows that the file was deleted with one pass. And so what happened here is that Red Salt actually overrid the Windows del command with its own delete command so that it can wipe the file for the operator. So our strategy for hunting for Red Salt was quite different than the strategy for the other malware because it was completely different. So in this case, we first looked for artifacts from the ACI shims. And Windows event logs were actually a goldmine for us because all of the executables that are shimmed using the inject DLL fix leave traces in the program telemetry logs. And in those logs, we saw the executables that were being shimmed and then their child processes. So what that means is that we were seeing the executables that the attackers were targeting, but then we were also seeing what the attackers were actually executing through the malware. So that was pretty interesting. Another IOC that we used was the firewall rule changes that the malware was doing. So when you told Red Salt to open a port on a specific system, then has to authorize that port in the Windows firewall. And when you add a rule in the Windows firewall, you have to provide a name for that rule. And it turns out that Red Salt used the same name for every single sample that we found, which dated several years back. Persistence-wise, we search for small SDB files. So SDB stands for shim database. So these are files which describe what the shim is supposed to do. We got some lucky hits, but we also got a lot of false positives, so that didn't work really well. And finally, Red Salt, just like the other malware, has a unique P export, which is start thread at winlogon. So we could search for that in memory as well, just like for the other malware. But we especially saw traces of that string in the first stage DLL stack string. So I'll come to that in a couple of slides. This is a dump of one of the hosts that was infected with Red Salt. So you can see here the Windows program telemetry logs that we were seeing. So on the top, you see the executable that is being shimmed, cvpnd.exe. And then all the other rows on the bottom are all the executables that the attackers are executing using Red Salt. So I'm not sure the attackers actually knew that we were seeing this when we were doing our engagement. So that was pretty nice. For the stack string, so if you recall, the first stage DLL was mostly junk code, and then some little bits and pieces of code would load a second file and execute that second file. The way it would execute that second file would be to call the P export of the DLL. And the attackers made a mistake there because they did not encrypt the string representing the export that they were supposed to call. Instead, they basically built the string on the stack. And we just had to take the static portion of those stack strings, remove the displacement, and we had basically a YAR rule or regex rule that we could use to find all of these stack strings amongst the whole environment. And that enabled us to find all of these samples on the top right, which you can see here. A few words on encryption. So Red Salt encryption uses Blowfish. Since they have a raw socket and they're getting all of these packets on Windows, they need something fast to decrypt all of the incoming packets. So Blowfish is a pretty fast algorithm. It uses two hard-coded keys, which I called K1, K2. The keys have not changed since several years as well, so this is good for us. For the C2 communications, it uses a combination of both K1 and K2 for some obscure reason. And for the door knocking mechanism with the passive mode, it uses only K1. The reason that it has different keys is probably because they want to be able to update their C2 keys with the newer variants of Red Salt while keeping the functionality of compatibility between the older variants and the newer ones on the door knocking mechanism. Finally, Blowfish has a small block size. This is going to be important for the next couple of slides. It's an 8-byte block size, so this makes it easier for us to find potential snort rules to hit on. If the attackers had used AES, for example, with a 16-byte block size, most of our snort rules would not have worked.
So what we had here is a combination of all sorts of decisions which together created, let's say, a vulnerability from a detection perspective, from the point of view of the developers, right? So as Adrian said, the fact that they selected Blowfish, which has a really small cipher block size, together with the fact that they decided to add the padding at the beginning of the data being sent, right? Together with the fact that they decided then to write down this job_no equal sign, that all of those decisions together from a developer perspective meant that it was really easy for us to actually calculate all the possible variations for the first encrypted blowfish cipher chunk, right? So coupled to the fact that, from all the samples that we've seen, they've never changed K1 or K2, so we could predict the encryption key. We basically calculated all those variations, encrypted all of those, and built snort rules for all of those, which meant that now we could detect platinum, or in this case, red salt over the wire, no matter what C2 IP that we're using. Now, for internal communications, the algorithm was slightly different, right? Here they decided to follow up the padding with the campaign ID or campaign password, right? So for our own engagement, this wasn't really a problem because we had already fully reverse engineered the sample. We knew what the campaign ID or campaign password was for our own customer. So we could do, just what we said in the slide before, which had to just write all the possibilities for that, first blowfish chunk, encrypt, build snort rules, and we're done. Now, what happens if we don't know the campaign ID or campaign password, right? If we want to do a more generic detection rule here. Well, again, because of an incorrect implementation of padding, right? There is one possibility which we call the lucky hit, right? If basically they determine that they need 8 bytes of padding, taking into account the block size is 8 bytes, they really don't need any padding at all, so there should be no padding. But because of the way it's implemented, they will go ahead and put 8 bytes of padding in there. So whenever that happens, we don't care what the password ID or campaign ID is, we can actually, detect that, which was really handy.
So going further, once we had exhausted most of our IOCs for the other malware, we tried to find for some other ways to hunt for this attacker in the environment in case we had missed anything. And so you might have noticed that some of the malware, all of the malware actually were packed with a custom packer that we had never seen before. So we thought it might be a good idea to try searching for this packer everywhere in the environment. So the packer was pretty well written, very well written. I won't go into the details, but basically, here's to illustrate two samples that are packed. And on the left and the right, the exact same actions are being performed. So computing a string kernel32.dll on the stack. But actually, the instructions are different, the constants are different, and the registers are different. So what that means is that the machine code to do this is completely different for both samples. So how do you write a rule when you don't have any common patterns to hit on, to base your rule on? So we did find some slight patterns, fortunately. This is an extract of the rule that we wrote. So this is basically for the 32-bit packer based on the ESI register. So we had to write several ones of these for each register, and then a 32-bit one and 64-bit one. And we had to translate that into regex. To be fair, a couple of months ago, I went over this, and there's actually a much simpler rule now, just one line to find this packer. But at that time, this is what we had to work with, and it was pretty difficult to search for this in the environment.
Yeah, so we had these YARA rules, multiple of those for all the different registers. So we had to basically use that for hunting, right? So what we did was we converted all of that YARA into regular expression so that we can search for that using HX quickly. We also had to limit the sweeps to only target portable executable files, and this was because we had a very sensitive customer from an impact point of view, so we had to minimize the impact of the sweeps on ongoing operations. But it took time, but eventually it worked, and it worked really well. It worked so well that all of a sudden we had platinum activity both on domain controllers and on all of the Exchange servers, which we had not seen before, right? We also found additional red salt and red curry, and we found two major components of platinum, which we call red mail, and red saffron, along with some other minor utilities, which we don't have time to go into on this presentation. So I just said we found additional red salt and red curry, right? This was shocking to us at that point in time, because we thought, hey, we have all these IOCs, all the different hunting strategies that I walked you through at the beginning. How is it possible that we're still finding more samples from red salt and red curry, right? We should have already found everything, right? What's going on here? The reason is we were finding the old stuff, right? The breach had gone on for so long, we had multiple generations of red salt and red curry and all the other ones in between. So that's basically what happened. We're hitting now all the old stuff, right? For example, in the case of Red Salt, what we were finding now was persisting using COM in WinLogon events, so it's completely different. There was no first stage DLL with stack strings for us to actually go ahead and find. And in this case, we could have used the Firewall IOC sweep, but we just hadn't gotten to actually, triage all those hits yet. And in the case of Red Curry, something sort of similar happened. To begin with, it was not persisting, because as you'll see later, there was another piece of malware making this Red Curry persist, which changed everything, right? That meant there was no PowerShell event log clearing, because on the current versions, it's actually the persistence mechanism which also clears PowerShell event logs, right? So there was none of that. There were no base64 encoded files, and memory hunting was moot because, as you'll see before, all of these variants were no longer running specifically when mandate arrived on site, right? And we'll go through that in a minute. So overall, just a very humbling experience as to how complex it is to actually write, truly generic IOCs in an environment, right? For something like that. So into Redmail. Redmail, one of the most interesting pieces, but I think we've said already a few times in the presentation, really. Just one more. This is really a Microsoft Exchange transport agent, just interpreted as a plugin for Exchange, which basically receives a copy of every single email that goes through that Exchange server. This was registered in a file called agents.config, and it was called Microsoft Exchange ODB agent, so blending in fairly well, right? So how we found this? We found this because even though this has to be a .NET DLL, it was calling another DLL, which turned out to be packed using this Platinum packer, and that's how we found it, right? That DLL in our case was msdbn.dll, and it had two simple exports, one to process email and one to self-delete and clean after itself. There was a third file, which was more interesting, which was this .inf file, which turned out to be the encrypted configuration. And here is when things really got interesting, because what we saw here was the following. On the first versions that we identified, right, this was just a list of targeted email addresses, right? So basically, any email to or from that huge list of interest for Platinum, Redmail would make a copy of and encrypt it on disk. All right. Now, the more recent versions had more configuration options, right? And specifically, they added something they call blacklist to that configuration option file. Sorry, but when you actually saw the expressions that they were using on that blacklist, they were literally using that to filter spam, right? So just think about those operators, right? They have to deal with their own spam plus with the spam of everyone else they're reading emails for. That sort of shows you the level of sophistication that we're dealing with here, right? Anti-spam for the malware exfiltration tool. Anyway, so as I said before, when an email sent to one of those targets was received by the transport agent, it encrypted it, in this case using a 128-bit AES key, right? And that key was also encrypted and stored using a 1024 hard-coded RSA public key, right? So there's no way we're gonna crack that open. And finally, it could also execute commands that were sent from a list of magic email addresses. So the only thing they had to do, if they ever needed to send commands to these implants, and they couldn't, for whatever reason, do it from inside, they just had to send an email to any of those lists of email to the target list. And finally, just to get a bit more context, the first sample that we found was dropped in 2010, right? We did a little bit of digging, again, Googling around, and pretty much no one in the incident response community was even thinking about transport agents back in 2010, right? Which again sort of positions Platinum very well, I think. And finally, no exfiltration mechanism. This thing did not have the capability to send those emails anywhere, which was sort of strange. What was the point of that? And it didn't make sense, to be honest, until Red Safran.
So Red Safran is the malware that we found a little at the same time, which was responsible for the exfiltration of the data. So we found Red Safran on some Exchange servers. At that time, it went back to samples that were dropped in 2008. And also on some workstations, and the most recent sample we found was dropped in 2015. In all cases, the samples were packed, which is how we found them, basically. So Red Safran, you can basically see it as a malware orchestrator. So it's a malware to organize other malware. So they were using this to interoperate up to 10 utilities in malware in this environment. And it basically organizes the data exfiltration between every host that is executing malware. It also organizes commands that you can drop on systems that may be unreachable from the internet. Just like Red Salt, it communicates between, so several Red Safran implants can communicate between each other using raw socket pings. As a configuration file, encrypted using ICE, so yet another encryption algorithm that they use. And a helper utility, which was actually pretty neat for us, because we basically just have to type show config on the host where we found Red Safran, and it would give us the configuration file. So some sample configurations that we retrieved. In one case, on a workstation, for example, we saw Red Safran simply starting a keylogger and some other unrecovered malware. And then on the Exchange servers, we would see Red Safran starting a keylogger, starting the Redmail implant, and then sending all of that keylog data and those encrypted emails to a configured workstation, which was also running Red Safran, and which was forwarding that to another place elsewhere. So these are two snippets of the configuration files that we would see using the showconfig command. So on the left, you can see for example, working hours, directories for commands, for results, for storage. You can see that if it acts as a server, there's some probe ports and transfer ports that can be used. And if it acts as a client, then it has a target host name, which it has to communicate to using also a probe port and transfer ports. And on the right, you can see that in this case, Red Safran was configured to execute KB 2.1.8, and if you remember, KB was red curry. You have even the command that it was using to execute this malware, so run DLL32. And on the bottom right, you can see that it was also configured to execute GP 3.2.1, which was, in our case, Redmail. Now, when we tried building network signatures for Red Safran, we had to go into its encryption. So there's something interesting there. So in Red Safran's configuration file, there's a field called network encrypt key, which is basically a password, which in our case was always 32 characters long. And when Red Safran communicates to another Red Safran host, it takes that huge password and it appends to it some random bytes, 16 random bytes to be precise. And with that, it generates a network encrypt key. So it has 48 bytes of entropy, and it generates a 32-byte network key to encrypt the packet that it's going to send to its peer. And that packet contains a payload, the size, a flag, and a magic value. So it encrypts all of this using AES 256, and then it sends the encrypted packets with the random bytes to its peer. And the peer only has to take the random bytes and then go through the same procedure to generate the same network key and decrypt the packet. So pretty neat, right? Because basically this makes it impossible for us to write a signature because the keys used each time are always random. There's a huge weakness in their key generation, and this was pretty funny to find, because out of a 48-byte entropy, Red Safran only creates 6,000 possible keys, which is not much at all. So it's very possible for us to brute force packets that we're seeing on the wire to find some Red Safran communications anywhere. So this is suitable for target hunting, but it may not be for more general detection at every client where we're going.
So just a final piece here before we move on to some questions here. One of the interesting pieces that we found searching for additional components from Platinum using all the different strategies that we highlighted was this dropper here. This was uploaded to VT on 2010. And this was one of the magical pieces that we were missing, right? Because this was a dropper without a payload. So Platinum basically uses this component and says, I want to install this payload, right? Whatever file it is, and I wanted to deploy that using this persistence mechanism. And you could basically pick and choose at the time that we were dropping your piece of malware. Worth shout out, though, is the fact that we had WMI persistence there. This was uploaded to VT, so we don't even know when it was created. In 2010, right? Pretty much no one was talking about WMI persistence back in 2010. So again, sort of positioning Platinum as a threat group really well. So all in all, it was a really interesting threat group to chase out of our customer's environment. We learned a lot and we had fun, actually. It wasn't the only group. We were chasing actually multiple state-sponsored threat actors in this one, so everyone was in here, but this was one of the more interesting ones here to talk about examples of what we found from an OPSEC and skill level perspective. We named a few. You got the time triggers, the self-delete or suicide configuration in case the operator lost contact with some of these implants. The secure delete that we saw on the, we wanted to show in the demo what we saw on the screenshot finally. And things like blending in with working hours, the anti-spam filter. All of that basically positions Platinum very well, I think. We did find references to Mandiant, to our engagement on the key logs. So basically Platinum knew that we were going to investigate. And they basically stopped operations 2 days before we actually landed or parachuted in there. 2 days before, they literally stopped some of the malware, removed some of the malware. The last email that was intercepted and saved to disk was again created 2 days before we physically landed. So they knew we were coming. They was just hoping that we would just go there, find the Metasploit and Zeek, Shell, and P-Link guys that we were called to investigate, and they would continue. Unfortunately, that was not the case. They did go undetected for 9 years, and they would have continued, going below the radar had it not been for that other noisy threat group in there. Again, so very low profile. They do go and use intelligently public resources out there. Lesson learned for us, as I said before, not all IOCs are equal. It's not easy to build a truly comprehensive IOC or hunting strategy, and we've seen a lot of examples in here. Lesson learned for Platinum. Sometimes, hiding too well can actually make incident responders focus on you guys. And also, probably making crypto or using crypto correctly is hard, right? We've seen quite a few examples in here. Yeah. And that's what we have today. So if there's any questions, I think we might have time or not, maybe not.
1 minute.
Sure. So we have some mics up here in the center. We do have time for maybe 1 or 2 questions if you have any. So please make your way to the mics if you have any questions. And I'll go ahead and kick it off. From a data targeting standpoint, was it just the email that it seemed like the attackers were after, or was there different data that they were going towards?
So email was like the big one in volume, and there was definitely other bits and pieces of data flying out the window here. But as I said before, there were multiple different groups. So yeah, the overlap between all of those wasn't super clear at the end to be sure to say what this one in particular was targeting there.
Sure, understood. All right, guys, well, we appreciate your time. If there are, oh, we do have a question over here. Go ahead.
Hi, thank you. So it looks like Platinum knew you were arriving a couple days before you got there. They were able to at least attempt to clean up a little bit. But generally speaking, when FireEye wants to do a hunt for APT, how do you do it quietly so that they don't have a chance to clean up? What's your approach on that?
So it's a good question. So if we suspect the exchange environment to be compromised, we go through some other email. I've never done it myself, but I think we go through other email providers to communicate with the clients.
Yeah, so you definitely don't want to be voicing through the corporate email the fact that you're going to land there.
But other than the communications with the client, like when you approach their, before you bring your tools in, before the YARAs are pushed out, how do you approach a hunt?
So I would say it truly depends a lot on the threat actor that you're chasing. Most of the times, to be honest, it's not going to make an important difference, right? You just land there, you drop your endpoint EDR solution, we drop our network sensors, and that's going to be good enough pretty much for 99% of the threat actors out there. Even with the more sophisticated ones like Platinum, the only thing that they actually achieved was actually shine a spotlight on the fact that they were there when they tried to actually make a copy of our HX and HIP agent, right? So that is not going to change a lot. For some very specific threat groups, that you've chased maybe in the past, and you know that the first thing they're going to do is just burn everything and disappear, maybe yes, your question would be valid, and you, on that case, would make more sense maybe to start with network deployment before you start making changes on the hosts. If you know that, but it's a very particular scenario, right?
Thank you.
Make sense?
Great. Well, thank you again, guys, for coming up here and talking about this group.